My name is Ian Dennis Miller. In this presentation, I will be discussing the use of psychological regression models in agent-based modeling. The first part of this presentation is going to discuss the method for adapting psychological models of behavior to agent-based modeling. The overarching goal of my research is to study psychological phenomena. This typically takes place over the course of experiments that are conducted in the natural world, but sometimes it's useful to conduct some of this research in simulated environments. There is an abundance of psychological theory that is published in the literature, and a lot of this is represented using regression models, also called linear models, maximum likelihood estimation, and least squares. Ultimately, they amount to models of a psychological process. Linear models are represented mathematically, which is a shared language that facilitates communication and interpretation. Due to this mathematical representation, they are also well suited for being adapted to computer code. This amounts to a method for using linear models of behavior in agent-based models. The modeling framework I propose that this fits into comes from Railsback and Grimm's 2011 textbook on agent-based modeling. One of their approaches is called pattern-oriented modeling. Their general algorithm is depicted in this image that I reproduced from their textbook, but I'm going to quickly review the steps right now. It begins when we learn about some phenomenon somehow, maybe from the literature or maybe from experiments, but ultimately this enables us to identify a pattern of behavior that we want to examine. The next step is to propose theories for how that behavior might come about. There is a level at which the grand undertaking of psychology is to determine the theories that explain our behavior. Based on those theories, we construct agent-based models, and then examine the execution of those models to determine whether or not the model produces the pattern of results that we expected. The psychological literature is absolutely filled with these patterns of behavior, and on that basis, it struck me as being a great match for pattern-oriented modeling. The challenge would be to figure out how to adapt these psychological theories to a computational framework. I suggest that any model that relates to behavior is going to be suitable for agent-based modeling. Some psychological theories directly model behavioral outcomes. However, not all do. This is going to be a very domain-specific assessment in which either you or your collaborators needs to be an expert. Often, non-behavioral constructs are studied in psychology. For example, personality. In that case, extra work is necessary to somehow relate it to behavior. Let's quickly discuss an extremely oversimplified example. Let's say, for the purpose of discussion, that homophily predicts romantic relationships. The existence of a relationship is not exactly a behavior, so why don't we relate it to the behavior of starting a relationship? So let's hypothesize that greater homophily is going to predict the decision to start a relationship. Well, now we have constructed something that could be the type of behavior that an agent could engage in. At a higher level, what we're doing here is running a regression in reverse. Let me explain what I mean by that. The typical way that regression works is that you get some data, maybe you produce a scatter plot, and you can imagine a line that best fits the data. The deviation between the line and the data is called error. When we run this regression in reverse, we're going to begin with the linear model, and we're going to try to reproduce the scatter plot by putting the error back in. This error term is random, and so in that sense, the deviations are not going to be exactly the same as whatever originally produced the regression model, and that's okay. One of the reasons that's okay is because we're usually going to run these simulations many times, and we want the error to be random, not systematic. So it's preferable that the deviations are different each time we run this. The general method for adapting a linear model for use in an agent-based model is to first assess the model to make sure that it even has the right characteristics. The best models will have terms that have been centered and standardized, which means they have a mean of 0 and a standard deviation of 1. Then we need to identify the distribution of the error term. Typically this is Gaussian, sometimes it's Poisson. We also need to identify the parameters for our error distribution. In the case of a centered and standardized Gaussian model, the mean of the error will be 0 and the standard deviation will be 1. If our model matches these criteria, then we can extract the slopes and intercept from the regression equation. Each of these slopes corresponds to some important property that the agents need to possess or that they need to interface with. In some ways, the regression model specifies some of the characteristics of our simulation. Finally, the mathematical representation of this linear model needs to be implemented as ABM code. Whatever simulation package is being used, you've got to figure out how to sample from the right random distribution. Frequently, there's a function for sampling a random value from a Gaussian distribution or a Poisson. Now, ultimately, we need to derive behavior from the regression model that we're adapting here. One way to do this is to apply a thresholding function to the results of the regression in order to determine whether or not an agent should engage in a behavior modeled by the regression. This amounts to creating a Boolean function that returns true or false, and it answers the question, does the agent engage in the behavior, yes or no? This threshold function acts like a trigger for that behavior. When values are above the threshold, that's going to produce a true or a yes result to this behavioral trigger function. When the values are below, then the agent does not engage in the behavior. This threshold regrettably becomes a degree of freedom in the model. As a result, it's necessary to calibrate the threshold through a sensitivity analysis. The goal of calibration is to select the optimal threshold that recreates the pattern of behavior. I think it's not necessary for the threshold to be a degree of freedom if you have centered and standardized all the terms in your model, in which case I think the threshold ought to have a value of 0. But there are many cases, like for example when dummy codes are used, when this threshold will require calibration. Now that I've discussed the general approach, I would like to show a brief example that comes from my own work to illustrate how this might be applied. As part of my dissertation work, I examined a really great series of studies by Erickson and Koltas in their article, Corpses, Maggots, Poodles, and Rats, Emotional Selection Operating in 3 Phases of Cultural Transmission of Urban Legends. One of the key findings from that work is that disgusting urban legends travel farther. That result is actually a replication of a previous finding from Heath, Bell, and Sternberg, 2001, but I particularly like Erickson and Koltas due to the way they dissected the transmission process. In their studies, they provided participants with urban legend stories that were crafted to either be disgusting or not, and then they examined how many of those stories were shared to other participants in the study. However, importantly, in the laboratory study they conducted, all of the urban legend cascades trended towards extinction. They did, in fact, replicate the result that disgusting stories were more likely to be transmitted, but in all cases, progressively fewer stories were shared by subsequent participants. This is a different pattern of results than what we observe in the real world, in which some stories actually proliferate and accelerate instead of ultimately fizzling. So, as part of my dissertation work, I extracted the regression equation from Erickson and Koltas and used that as my model of transmission behavior in an agent-based model. With that theory of behavior, I was able to reproduce the original pattern of results using my agent-based model. However, my main contribution here is to go a step further in order to reproduce cascades that actually grow over time. I based my approach on pattern-oriented modeling with the initial goal of reproducing the Erickson and Koltas results. Their model predicted the intention to share a story, so I extracted the intercept and the slopes from that model. There was a term called disgust, whether the story was disgusting or not, and they had dummy coded that as being either 0 or 1. My preference would have been for that term to be effect coded as -1 and +1, which would have a mean of 0 and would be therefore centered. However, they didn't do that, and that's absolutely fine. It just means that we're going to have to calibrate our threshold. For those agents in the simulation who received disgusting stories, when computing whether or not to engage in the transmission behavior, the value for the disgust term is going to be equal to 1. As a consequence of the basic math that drives linear models, a disgust value of 1 produces a higher intention to share. I conducted a sensitivity analysis for the behavioral threshold, and I found a threshold that was half a standard deviation below 0. That was sufficient for producing the results you see in the image, which closely correspond to the pattern of results published by Erickson and Coltis. As I said earlier, the pattern of behavior that I wanted to see was that the disgusting stories should not die out over time. They should proliferate. That was not the result that was produced in the laboratory, but that is what we see in the real world. The general method I used was to take the model that I had just calibrated and transplant it into a new environment. I swapped out the serial reproduction network and replaced it with a scale-free network that I built using a preferential attachment algorithm. This new environment changed the network topology that connected all the agents. What you see depicted here is the pattern of results. The low discussed stories, the blue bars, taper off as stories are shared farther and farther, and the disgusting stories, the yellow ones, are shared at an accelerating rate. This is further evidence for the network implications of information sharing. By changing the network and nothing else, I was able to produce the pattern of results that we wanted to see. But I was also able to do so much more affordably by using a simulation instead of having to recruit a whole new set of humans and configure them into the right network and redo the study with those people. That would have been very expensive, and we would have needed a lot of people. Agent-based modeling made it possible for me to look at this network question. In conclusion, I suggest that this is a general method for examining social processes. The social psychological literature contains tons of models that are often linear models. Some of these models are theories of behavior, and some of those can be adapted for use in agent-based modeling. Now, in order to accomplish this, the regression equation should have terms that are centered and standardized. It's important to identify the proper error distribution, and typically it's Gaussian. Then, the regression model needs to be transformed into some kind of behavioral trigger, and I propose doing this by thresholding the function. One of the key benefits of this approach is that linear models are a common language among the sciences. This method facilitates collaboration between agent-based modelers and other types of scientists, including social scientists. Using agent-based models, it's possible to examine psychological theories in new environments, including environments that would be prohibitively expensive to study in the real world or that might not exist in the real world at all. And with that, I conclude my presentation. Thank you very much to the organizers of COMSIS 2019. I love the idea of a virtual conference, and I love the idea of skipping a plane flight. If you have any questions, please comment in the forum threads or reach out to me via Twitter at Ian Dennis Miller or through one of my websites where I have my contact information. Thank you very much.